All right. So today we'll study three very important concepts. And this concept of public key encryption, which we studied in last class well, has changed the world of encryption. Okay, so we'll elaborate on that. We'll look at two specific algorithms. Just a minute. Yeah. ElGamal and RSA encryption. Okay. So we have studied two kinds of encryption method. First was symmetric. Okay, where both sides had the same key. There's for example, Alice and Bob both use same key. So Alice will use the key to encrypt the text that she sends. She wants to send to Bob, and Bob uses the same key. The key is the same, right? So that's the reason we call it symmetric key. Second is asymmetric key, wherein keys are different, right? So Alice has a key and Bob also has a key. Bob has both have a keys called private key and public key. Private key and public key, right? Now we have seen this first, the one which we studied, the Diffie-Hellman, that was kind of first, and the objective is to exchange the key. Okay, once or come out with common shared key, like in the case which can be used for symmetric encryption, right? So after all the interaction, both had the same key. But here, and so there's also kind of asymmetric key encryption. But what we'll study today is that we'll work on that and then try to improve. Okay, all right. So I have taken this content, of course, from many sources, and the one which you can read is the Berkeley lecture on cryptography. Okay, they have also text, but it's very concise. Okay, if you want to get more details, because this is a very complex topic. Okay, this is a most complex topic of security, cyber security or information security. So you can read this book as well. This is a very nice book, Sam Mark's book, which is available. And then you can go through multiple video lectures. Actually, one lecture from MIT is quite good on public key cryptography. Just search and then you will get that lecture on YouTube. Or not necessarily YouTube, maybe MIT is some platform. So here we are. Okay, so we have completed symmetric encryption in total. We started with one-time pad, ciphers, block ciphers, and chaining of ciphers. Then we studied MAC, and then we studied HMAC. And then in the process, we have studied hash functions and also pseudo number generator. Diffie-Hellman we studied in last class. So we are here now. Okay, so we'll study today these two topics, RSA and ElGamal encryption. And the next class onwards, we will do digital signatures. And after that, we'll also study something that will ensure that public key, that Bob's public key that Alice uses a genuine key. Okay, so for that we'll see how can we achieve that. Right now we are assuming whatever public key is being sent is true public keys, right? Okay, so these are the contents. Okay, so we studied Diffie-Hellman. I think you remember it. Okay, idea of Diffie-Hellman is to come out with a common secret shared key. Okay, secret between both participants which are communicating with each other, like Bob and Alice. Okay, all right. So we take P as a large prime number. When we say large, it's really large. It's almost like 2000 bit number, right? 2048 bit kind of number. It's really big number. Okay, and then we take G is a generator. It's very small compared to P, and it's also chosen between 1 and P minus 1, where P is very large. Okay, it's a prime number. And then Alice could pick up So P and G is public knowledge. Okay, it's available, either published or Alice can send it to anybody and anyone can see it in between. So if in between, you know, say for example, Mallory is there, Mallory can see it. Okay, so nowadays G and P are hard coded. All right. So now Alice picks up a random value, secret value A between 0 to P minus 2 and computes A is equal to G raised power A mod P. Note that here A is a public key of Alice and A, small a, is a private key. Similarly, Bob does the same thing. He picks up random value B, which is a private key. And then this capital B is public key. So now public key can be announced to anybody or it can be published in some source somewhere. Okay. All right. All right. So this is what we have done. Okay. So now if Alice wants to send something to Bob, say message M, then she can use Bob's public key. I'm sorry here. I'm so sorry here. We are in Diffie-Hellman. I'm so sorry. Okay. I'm so sorry. Okay. So now, okay. So Alice now uses her knowledge of B, which is public key of Bob, and A, her own private key, to come out with shared secret S, which is G raised power B A mod P. Similarly, Bob uses knowledge of A, which is Alice's public key, own private key, come out with G raised power A B, which is same as here. So both have the same result as. Now they can use this shared secret, which is known only to two of them. Okay, because of this kind of relationship between private and private key and public key. Okay. All right. So that can be used for further communication, symmetric key encryption, symmetric crypto system. All right. Okay. So this is the algorithm that we studied, that Alice private key, Alice public key. She communicates only public key, which is the same as this one. It's received here. Similarly, Bob generates private key and public key. Public key he sends to Alice. Alice receives it, and both do the computation and come out with common key. Okay, this is simple. All right. So of course we are not. When I say simple, it looks simple, but if you really get into proof, then you'll have to understand the complete mathematics behind it, right? And those of you who are smart in mathematics and want to spend time, please go to look at any book and then try to understand how it works. Okay. All right. We don't have time, and also it's really out of scope because we'll take another 2-3 classes to go through all the proofs of the, not only about this algorithm, but the other algorithms that we'll study. Okay. So now here, only thing is that prime number P and G has to be agreed upon. Okay, between the two participants. Okay, and in practice, P is very large. Okay, usually 2048 bits size. It is a very large number. Okay, 2K number is quite big, right? I mean, it's so it can have large number of combinations, right? So 2 raised power 2 raised 2048 minus 1. It's quite big number. So 0 to this much, right, is the range. And of course, from that, P and G has to be randomly picked up. Okay, which is P is a large prime number. So, but these are to be announced. So when, I'm sorry, it's not really random picked up, it's just picked up, and then of course the public knowledge. So nowadays, of course, algorithms come out with P and value of P and G embedded into it. Okay. So if you want to get more details on how key length is, what is the key length currently in use this website. Okay, so we have studied Diffie-Hellman. This was the original algorithm, and then same property, because what we have used is a group theory, right? Okay, we have done modular mathematics, right? So there can be many mathematical functions which will have similar property. So we find that researchers have found that elliptical curve also exhibits similar property. Okay, and then so we'll look at some details of this in subsequent slides. Okay, so this P number is 2048 bit prime modulus, and usually P is this number. Okay, and generator G is chosen to be 2 in when we talk of practical applications, because anything raised power of 2 is very simple for machines to calculate, because every number, most of the calculation that we do, as we have seen in case of when we studied computer architecture, we see is raised power of 2. So whole calculation of calculation like multiplication, division, it becomes very easy. Okay, and because P is of 2048 bit size, the both public key and private key are of the same size. Okay, now note the difference between keys used in Diffie-Hellman or asymmetric key encryption versus symmetric key encryption. Symmetric encryption key size is very small, okay, compared to this. What was the key size used in symmetric key encryption? Anybody can remember? Any idea? 128, 256, what? No, 256?
Yes, sir.
Around this, right? I mean, AES, DSO, different algorithms will have different sizes, but generally it's very small. And because of this, the whole calculation is also very long, right? It's a lot many steps. So doing encryption using public key encryption method is very complex. It is time consuming. While in case we'll come out with this point little later. Okay, and then we have seen that it's not only Diffie-Hellman, that if two functions that we have seen here, this function, right, can only be used, but elliptical curves can also be used for key exchanges, right? Okay, so different kind of groups can be used. So this algorithm can be implemented different kinds. Now group theory, if you study, then you'll learn about it, right? What are different groups, right? We have simply seen modular group, right? One using modulo function where number repeats. So there can be many ways, right? So a group can be made from elliptical curves. So ellipse we have already studied somewhere or other, right? So in school. So now advantage of elliptical curve encryption is that the key sizes become smaller, so around 256 bits. Okay, and there are various kind of elliptical curves. So like P256 curve, 255, 19, and so on, which have 128 bit of security. Then P521 curve 448 has 256 bit of security. So you don't need to really get into details of this. If you're interested, of course, you can go and find out what these curves are. Okay, so only point I want to emphasize here is that based on elliptical curves, Diffie-Hellman algorithm can be extended. Okay, and with the similar properties of key exchanges. And Diffie-Hellman with Diffie-Hellman advantage that key sizes can be smaller. Okay, so read it if you're interested. So that's all I wanted to talk about Diffie-Hellman. So Diffie-Hellman, we have public key and private key. Okay, similarly Bob will have same public key and private key, but whole exchange of information between the two is come out with a key, shared key, which can be used for, once the both have parties have same key, then we can use it for symmetric key encryption. All right. Okay. That's one advantage. However, it has many disadvantages, that until the shared key is not available, then communication cannot happen. Okay. Okay. So, and second thing is that you have to really depend. You only thing that left out is that you'll have to use that key for encryption. Okay. So now other third process is that why not use the public key of, suppose, I'm sorry, if Alice wants to send a message to Bob, why not use Bob's public key directly to encrypt a message that only Bob can decrypt? So there's a difference earlier, right? So we have done Diffie-Hellman, we have ultimate aim is to come out with shared key. Now that shared key can be used for encryption. So Alice will use shared key for encryption, which Bob will use for decryption. So instead of that, just think that Alice has Bob's public key because of public knowledge. So Alice can use Bob's public key for encrypting message she wants to send, which Bob's can decrypt. Okay, it's like okay, you have you seen? I'm giving a very crude example here. Okay, have you seen the small locks that are available, which you press, then it locks? Okay, very small size lock you would have seen. You know, kind of this kind of lock, and there is a small what do you call that? Hook kind of thing. So if you just press this, then it locks up. But the only person who can open is who has the key. Okay, so basically this lock is given to Alice. Alice will put everything, you know, in a box, and then on top of box you'll simply have this lock. Okay, and then using Bob's public key. Bob's public key is nothing but it says a press the, what do you call that, hook. Okay, and then it gets locked, and then only Bob has private key, which he will insert and then open. So we are coming out with that kind of scheme where anybody can use Bob's public key for encryption, and only Bob can use private key for decryption, right? So that's called public key cryptography, this type of asymmetric key cryptography. Okay, so we have the concept that we know by now, there is a public key and private key. Okay, so every participant will have two keys. Okay, and then of course we have, it's based on, of course, number theory, and we have already seen discrete logarithmic problem, but other examples are modular arithmetic and factoring. In contrast to symmetric key encryption, wherein we use XORs and bit shifts. Okay, if you look at the design of AES or DS, you'll see XORs, exclusive ORs are used, and bit shifts are used. And note here, the messages are only numbers. Okay, if you have text message, you have to code it as a number. Actually, it becomes a number. Anything in computer actually is a number. In contrast to symmetric key cryptography, which works on bit strings. Okay. So advantage is that we no longer need to assume that Alice and Bob already share a secret key. Okay, all right. And drawback is much slower than symmetric key cryptography because it's compute intensive. So to repeat, every participant has to split a key, or basically instead of having one symmetric key, it has, person has two keys, a public key and a private key. Okay, public key is used for encryption and private key is used for decryption. All right. Okay, so the first step is usually key generation process. In the key generation process, each participant generates two keys, a public key and private key. Okay, that we have already studied. So if Alice wants to send a message to Bob, so Alice, Bob. So Alice has a message M. She can encrypt using Bob's public key. Okay. And she sends this encrypted message to Bob. Bob will use his private key to decrypt the message M. All right. So this is the way it happens. Okay. So now it means that here is Alice. Okay. Anybody can send a message to Alice provided the person knows Alice's private key, public key. If Alice has public key, she can publish in her website or where this is my public key. Okay, so anybody, maybe it's a Trudy or Bob or anybody, can use the Alice's public key to encrypt the message and send it to her. Okay, if anybody in between sees the message, cannot do anything because person will not have Alice's private key. All right. Any question? No? Simple? All right. So now to repeat, everybody can encrypt with the public key. Like here, everyone has encrypted using public key. Whose public key? Not person. You know, if this is Trudy, so not Trudy will not use her own public key. See, if I am sending a message to you, I will have to use your public key, and then you have that message you will have to use your private key. Okay. So when we say that everybody can encrypt with public key, this is the recipient's public key. Okay, not own public key. Okay, and then only the recipient can decrypt with the private key. Okay, all right. So again, pictorially, we can see that first step is generate private key and public key, and these keys are generated based on some parameter, what is size of the key and so on and so forth, right? And there's an algorithm to generate these two keys, and these are not independent. It means that they are dependent. Okay, some relationship, some magical relationship which will finally let person decrypt it. Okay, so the Alice's public key is known to everyone, and then message is sent to her encrypted with the public key, and you will use a private key to decrypt it. Okay, so that's the relationship is shown here. So Alice wants to send a message to Bob, she has to use Bob's public key and use her message, whatever she wants to send, use encryption method. Okay, using Bob's public key and encrypt the message and then send it to Bob. So Bob has this message available and he has his own private key and use private key to get the same thing which Bob Alice has sent, which is message M. Then Bob will also get message M. Okay, any question? Are you able to understand the difference?
Yes, sir.
Okay, all right. So I'm trying to give the same concept in multiple times using different diagrams because once you understand it, it's easy to remember. Okay, so basic algorithm has 3 parts, which you know by now. First is key generation. So key is generated, okay, based on some parameters, which is PK is private key, public key, and SK is secret key. Okay, secret key is nothing but private key, and PK is public key. All right. So every participant will generate this. Okay. Note that now there is no one-to-one communication, right? So it could be many people may want to send a message to Bob. Okay, as if they know Bob's public key, they can encrypt the message and send. Okay, so it's like a letterbox, right? In front of your home, you put a small letterbox. Okay, letterbox has a lock. Okay, and only it's your home, so only you have a key of that lock. So anybody can put letters into the letterbox. It can come from anybody, and only you can take it out. Okay, so this is the first step. Generate two keys, PK, SK. Okay, and then second step is encrypt message M using public key of the recipient. Okay, and next step is that to decrypt this message, recipient uses secret key or private key, and then this ciphertext that he or she has received to get value of message. Okay, all right. So three properties. So its properties are correctness. Okay, so what message is being encrypted after decryption, it will get the same message back. Efficiency, it should be fast, and security, it should be similar to IND CPA. All right, so let's look at again pictorially. Okay, so Bob generates two keys. Now I've changed the notation slightly. Bob, so I say is a public key of Bob. This is secret key of Bob. Secret key is nothing but private key, which only Bob knows. Okay, now Bob can only send public key, so he sends public key to Alice. Alternatively, he can publish in somewhere, or he can register it with third party, and from there everybody can come to know what is Bob's public key. Okay, so nevertheless here Bob sends public key to Alice, and right now I'm assuming that public key is reached properly to Alice. Okay, what Alice will do now, Alice wants to send a message M, and she will use Bob's public key to encrypt, and the ciphertext is C. She sends ciphertext to Bob. Bob will decrypt it using his private key. Okay, and get the message M. All right. All right, so this is what you discussed in at very top level. This is how it happens. Now the question is, how do you implement this, right? So there are various algorithms. Of course, this is for key exchange. Again, I mean, I'm not giving you specifically for public key encryption. So basically, asymmetric key encryption are based on three methods: discrete logarithmic scheme, integer factorization schemes, and elliptical curve schemes. Right? This we have seen in brief. Okay, Diffie-Hellman we have seen, logarithmic scheme we have seen also in brief, which is largely for key exchange. Now what we are going to study is ElGamal method, which is small tweaking of Diffie-Hellman algorithm. So you can see that basically Diffie-Hellman algorithm does most of the job. Okay, but little bit of tweaking we can come out with algorithm which can be used for different kind of applications, right? Okay, the one which we have, the way we have studied here, right? This one. That a person wants to send a encrypted message, only needs to know public key. So we are not talking about generating a common key, right? Okay, and you can go through this diagram, this tags, right? Okay, so this requires arithmetic with, in general, public key encryption requires arithmetic with very long operands and keys. Longer the operand and keys, more secure it is. Okay, so we can see if algorithm with security level n will have a key length of n bits, right? So we can see that Okay, like RSA that we'll study now will have 1024 bit or 3072 bits or 15360 bits. It's quite large size, right? Similarly, symmetric in comparison to public key, you can say symmetric key sizes are generally small. 80 bits, 128 bits, 192 bit or 256 bits, right? Okay. All right. So basically, public key encryption is different than symmetric key encryption. Like, and we will see how we can use it for key establishment and digital signatures. We'll study in next class. However, they are slow. So because the computing intensity is very slow and bulk data encryption, we cannot use it. For small exchanges, we can use public key encryption method. All right. So now we'll come to ElGamal encryption method, which is a kind of one of the important public key encryption algorithm. Okay, this is where we are. All right. So we have seen why not use Diffie-Hellman directly, because all we can do is that exchange of symmetric key. Okay, basically, sorry, we can come up with asymmetric key, and then symmetric key is also not, a participant cannot control the symmetric key, because is symmetric key comes out with combination of public key, private key, etc. of both parties. Okay, and so nobody can say what the symmetric key would look like. It depends on private key of Bob and private key of Alice. Okay, and public key of Bob and public key of Alice. So it's a so we cannot control it. Any participant cannot control it. Okay, all right, and they cannot send an encrypted message of their own, like we have seen, because ultimately with Diffie-Hellman we come out with a common key. Okay, unlike a public key encryption where anybody can use Bob's public key and then send message to Bob. All right, so it works as follows. You'll see similarity between Diffie-Hellman and ElGamal. So take public parameters P and G, whereas P is very large prime and G is generator. And then Bob chooses value B between 0 and P minus 2. Okay, and computes B, which is G raised power B mod P. Note here B is Bob's public key, and this small b here is private key. Is very similar to Diffie-Hellman. Okay, the Bob publishes B to the world and keeps small b secrets fine because the private key. Okay, now Alice has this B and wants to send a message to Bob. Okay, which is message is M. Now note that we know that message has to be a number, so it has to be in the range 1 to P minus 1. And note that P is very large number. Okay, so Alice picks up a random number R. Okay, whereas R is in the range 0 and P minus 2. What will she do now? Alice form a ciphertext as follows. She now this ciphertext has two numbers. First number is G raised power R mod P. G is generator number, function number which is known to all, is usually 2. R is a secret that Alice has. Mod P is number known to everyone, and then she does this one. M, she multiplies M, note M is a number, with B raised power R. What is B here? B is Bob's public key, which she has received. R is a small number. R, so not, I shouldn't say small. Bob is, R is a number which she is using here. Okay, all right. Okay, okay. Now Bob receives this one. Sorry. So this is what Alice sends. So it's a pair of numbers, right? It's in this form, R and S. Okay, Bob receives this in this form. It just receives two numbers. Bob doesn't know all these calculations, right? So what Bob has to operate on these two numbers. Okay, so this decrypt this message. Bob does R minus B. Note B is Bob's private key. Okay, and S mod P into S mod P, which is same as this number, to get value of M. Now you can calculate and see whether it verifies or not. So R is this one, S is this one. If you do multiplication of M, if you do this, R minus P, so we'll get R minus P into S, which is equal to R is equal to G raised power R minus P into M into B raised power R. So this turns out to be M mod P. Okay, same as, so it decrypts a message M, which is sent by Alice. So it's basically a small tweak to ElGamal, Diffie-Hellman. Okay, so to summarize, basically we have three functions: key generation, encryption, and decryption. All right, simple. Same thing that we have discussed earlier is mentioned. Please go through it. Okay, so its security is same as that of the Diffie-Hellman algorithm. Okay, is it IND CPS secure? No. So I will ask you to find out why. You'll have to revise the concept of what is IND CPS security, because there is a determinism. It's all deterministic. Okay. Okay. Non-determinism or only secrecy comes because of use of key. All right. And system parameters, P is usually large, 2048 bits. G is usually taken in the range 2 to P minus 2, and so on. All right. Any question? Okay, you don't need to get into too much of detail at this point in time. Try to understand how it works. It's basically a magic of number theory. Okay, all right. So let's look at another example, another algorithm, again in very brief, but uses different arithmetic. Okay, okay, this is called RSA. Note that there is these three people were very famous scientists. I think from MIT or somewhere, I don't remember. And there was a company called RSA just 10-15 years, but it got acquired by some other company. The large public company worked on security. All right. So basically, three scientists, Rives, Shamir, and Edelman, they came out with a solution, and you can see that it's possibly MIT. Okay, and this is the oldest one. Okay, although we have studied all this, like we started Diffie-Hellman and then ElGamal. So RSA was the first to come. Okay, and it was most popular, and it's heavily used for digital signatures, which we'll study in the next class. Is mostly used for encryption, a small piece of data, especially for key transport. Okay. So, and RSA encryption, as we have seen in case of public encryption, is several times slower than symmetric encryption, which is AES. All right. So main use of encryption feature is securely exchange key for symmetric ciphers. Okay, which of course you can achieve with Diffie-Hellman algorithm also. So it's based on integer factorization problem. Okay. So now note that multiplying two large numbers is computationally easy, but factoring the result is very hard. Okay, so calculations are based on these two theorems, Euler's theorem and Euler's 5 function. Okay, please go through it if you are interested. So it was the world's first public key encryption. Okay, is based on difficulty of finding prime factors of large integers. Okay. So main idea is analogy is that Bob is able to implement a digital lock which only he has the key, makes his digital lock public. He gives Alice or anyone the way to send him the secure message which only he can open. Okay, so basically two public keys he will have, public key and private key. Two keys he will have, public key and private keys. So Alice wants to send a message to Bob. She encrypts the message with Bob's public key and Bob decrypts the message with the private key, his own private key. So let's look at this algorithm in detail. P and Q are large prime numbers, usually are in 512 bits, each of 512 bits. As a result, you get N is equal to P into Q. Okay. E is a relative prime number. You know what is a relative prime? It could be any prime number, okay, such that GCD of E and P minus 1 and Q minus 1 is 1. Okay. So E is relative prime number to P minus 1 and Q minus 1. Okay, typically E is chosen to be this number. Okay, so now once you have chosen P and Q, then you come out with N. Okay, and then you choose a relative prime number E, which is relative prime to P minus 1 and Q minus 1. Once you have these two, N and E, then this forms your public key or Bob's public key. Okay. Now somebody encrypts a message using N and E, then Bob can decrypt it using D. Okay, wherein D is inverse of E. So E and D is equal to 1 mod P minus 1 Q minus 1. Note that we have studied inverse in modular function. Okay, so here E and D is equal to 1. So D is nothing but inverse of E. Okay, all right. I'm sure that you will find it difficult to understand right now, but please go through the slides again and read book. You will have better understanding. Okay, now Alice wants to send message M to Bob. So she gets Bob's public key, which is N and E, and she has a message M, which is a number, and which is less than modulus N. Okay, now Alice encrypts a message M as, okay, so M is a message she wants to encrypt. So she will take M, which is a number, then raise power E, because E is in Bob's public key, and do mod of N, that becomes C. Okay, and Bob receives this message, he can decrypt it using C raised power D. D is his own private key, and mod N, and get the message, original message M back. Right? So that's the theory. Now let's look at one simple example, and again this is not complete. Okay, because again you, in order to even do calculation, you need some knowledge of theorems. Let's take P is equal to 7 and Q is equal to 11. So N becomes 77. So P minus 1 into Q minus 1 becomes 60. Okay, all right. P minus 1 is 6 and Q minus 1 is 10. 6 times 10 is 60. Okay, now we have to find E, which is relative prime to 60. Okay, now E is chosen to be 37, which is relative prime to 60, such that GCD, greatest common divisor, between 37 and 60 is 1. Okay, so now from this Bob can form a public key 77 and 37. This N and this E. Okay, so now Bob has to find out his own private key from this one. Okay, so using extended Euclidean algorithm, can find out E into D is equal to 1 mod P minus 1 Q minus 1. So E is 37, 30 times 37 into D is equal to 1 mod. This is 60. If you solve for this inverse of 36 with mod 60, you will get D is equal to 13. So this is Bob's private key. So Alice wants to send a message which is 2, number 2 to Bob. So she will calculate a ciphertext C is equal to M raised power E. Now E is given in Bob's public key, so it's known, which is 37. So M is 2, so she will calculate 2 raised power 37 mod 77, because N is 77 here. And the result is 51. So she sends 51 to Bob. So Bob, to decrypt it, Bob will use C raised power D, that is 51 raised power 13 mod 77. The answer will be 2. Okay, so it looks like a magic to us, right? But there is a mathematics behind it, so which you can read from any book if you're interested. All right, so do this self-reading of second example or read it from the book. So RSA encryption summary, basically we have, is based on, slightly different method. Okay, is based on plain number theory. So I'll take two primes, large primes, P and Q, calculate N. Okay, and this number of bits in N is usually large, between 246 and 4096. So it's very, very large number of bits. So N is very, very large. So P and Q are also large. Choose E is called, choose one E, which is relative prime to P minus 1, Q minus 1. Okay, and from that you come out with inverse of E, which is D, with mod P minus 1, Q minus 1. So you can come out with this a private key. Okay, so now public key of Bob is N, E, and private key is D, and anybody can encrypt using N and E. Okay, so and Alice uses her own message M, and the decryption can be done using C raised power D mod N, which is ME raised power D mod N. Okay, so now only issue with this RSA algorithm is it's not IND CPA secure. There's no randomness at any point excepting for key generation. So yet it's secure. IND CPA secure is very strict form of security. Okay, if the Alice sends same message multiple times and Bob encrypts it, sends it back, it should not. Every time it should be different, right? Something like that. Okay, all right. Okay, so this all we have done. Okay, all right. So this, what we can do in just 1 minute is that, see, we can use in Diffie-Hellman we have directly generated key, but we can now use this to generate a key. Okay, so for example, Bob sends his public key to Alice. Okay, okay, and Alice generates a symmetry key K. Okay, now it's Alice's responsibility. Earlier in Diffie-Hellman, both have collaborated to compute symmetric key. Now Alice generates symmetric key and she encrypts it using Bob's public key. Now this encrypted public key goes to Bob, and Bob uses his own private key to decrypt it and get the symmetric key. Now it's simple, right? Very simple. And then can use the symmetric key for symmetric encryption, like AES. Same thing we have depicted. I have taken this diagram from David Wong's book. So you can see that first step is to generate symmetric key, like Alice generates symmetric key K. Okay, and then encrypt the symmetric key using okay, this is Bob, here is Alice. Okay, so using Alice's public key, and that Alice can decrypt it using her own private key and get the symmetric key. So this symmetric key is same as a symmetric key here. Okay, and then both can communicate using this symmetric key. Simple. All right, so that's all. Okay, thank you. Any question? I know I have rushed fast, but please go through the slide set, you will understand it. If you understand the concept of asymmetric encryption, public encryption is just good enough, and details you can always find out. Okay, any question? Now, one question that you can ask is that if Mallory in between finds out the public key she knows, right? But if she is a man in the middle, she can change the public key. Bob is sending public key to Alice, and then Alice can change the public key and send some other public key, create a public key and send. And similarly, whatever message Alice sends to Bob, she can intercept that and then use her private key to decrypt it. So that's possible, right? So that's one question we'll try to answer. All right, thank you then.